Hi everyone, welcome to Lecture 14, Part 1 on the direct method of agreement. The objectives for this video are the following. After watching, everyone should be able to, number 1, describe the direct method of agreement, and number 2, apply the direct method of agreement using property tables. So there's only two objectives for this little Part 1 video. This lecture and the next three will look at these things called Mill's methods that are in the text. They're called Mill's because John Stuart Mill presented them, although I don't think the methods originated with him. And they're called methods because they are designed to guide an experimenter in their search for causes. Remember, we're talking about cause and effect for the next few lectures. We'll look at 5 different methods over the course of this video and the next 3 videos. Now this material spans quite a bit of the textbook, and there's a lot of example tables and text in those pages in the book. So to help kind of organize that mass of information, here's a little table that summarizes what we'll be seeing. Roughly each of the methods are used to find suspected necessary conditions or suspected sufficient conditions, or both, of a given property. And indeed, as we'll see, sometimes you can say something a little stronger than just a method tests for necessary and sufficient conditions. And the methods do this by a process of elimination. Now we'll fill in this table as we move through the videos about the different methods. The names of the methods are what you can see there. I don't, at this point, want to overload people with things to remember now about stuff that we haven't met just yet. So what we'll do in each video is introduce the method, we'll say what it's designed to do, so we'll fill in that right-hand column in the table there one by one, and then we'll go through an example or two of how each method works in practice. So in this video we'll look at the direct method of agreement, which is in blue up there, and we'll apply it to some examples. The next 2 methods will be covered in the next 2 videos respectively, and the last 2 methods will be covered together in the 4th video in this little mini-series on Mill's methods. So, to the direct method of agreement. The direct method of agreement is a method for narrowing down the possible necessary conditions of a given property. So to begin with, let's get a bit of terminology on the board. We call the property whose necessary or sufficient conditions we're looking for the conditioned property. And those properties that we suspect of being necessary or sufficient conditions for a given conditioned property, we call the possible conditioning properties. The conditioned property might have more than one necessary or sufficient condition, of course. In this video, we're concerned only with looking for necessary conditions for a given conditioned property, because that's what the direct method of agreement allows us to do, allows us to look for necessary conditions. In particular, the direct method of agreement tells us how to eliminate certain conditions as necessary conditions from a list of possible conditioning properties that we start with. Now, to apply the method, we'll use tables to record the presence or absence of the properties involved, and we'll make our conclusions using the tables. So let's get some examples in play. Suppose that we have 4 possible conditioning properties, A, B, C, and D, that we suspect of being a necessary condition for the given conditioned property E. And suppose that we record a set of observations on 3 different occurrences, like this. So we have the possible conditioning properties in the table and the conditioned property in the right-hand column. And then the problem, or the game, is this. Given some observations, what does the table tell us about which of the possible conditioning properties can be a necessary condition for property E? Now, remember the definition of a necessary condition. Last time we said that a property P is a necessary condition for a property Q, just in case whenever Q is present, P is present. So using this definition and the table, we can deduce some information. So suppose we record a series of observations as an occurrence in the table, and we do so like this. Here the series of observations is recorded as occurrence 1, And in occurrence 1, A, B, C, and E are all present, while D is absent. And suppose further that we record a second occurrence, occurrence 2, in which A, C, D, and E are present, but this time B is absent. And suppose that we record a third occurrence, occurrence 3, in which B, C, and E are present, but this time A and D are absent. Now, once we've filled this in, we can start to make a few inferences. Now, occurrence 1 tells us that D cannot be a necessary condition for E. If D were a necessary condition for E, then by definition of necessary condition, whenever E is present, D is present. But what does occurrence 1 tell us? In occurrence 1, E is present, but D is absent. So occurrence 1 tells us that D cannot be a necessary condition for E. So occurrence 1 eliminates D from our possible list of necessary conditions. In exactly the same way, occurrence 2 tells us that B cannot be a necessary condition for E. If B were a necessary condition for E, then by definition of necessary condition, whenever E is present, B is present. But in occurrence 2, E is present and B is absent. So occurrence 2 eliminates B from our possible list of necessary conditions. Now have a look at occurrence 3, and you might want to pause for a second on the video because there'll be a question coming up. So here's the question: what does occurrence 3 tell us? Occurrence 3 tells us that A cannot be a necessary condition for E. If A were a necessary condition for E, then by definition of necessary condition, whenever E is present, A is present. But in occurrence 3, E is present and A is absent. So occurrence 3 eliminates A from our possible list of necessary conditions. And occurrence 3 also tells us what occurrence 1 already told us, that D cannot be a necessary condition for E either. So after we've looked at all occurrences, the observations show us that if one of the possible conditioning properties is in fact a necessary condition for E, then it must be C. C must be that necessary condition. Now, the example we just looked at involved only simple conditioning properties, but we can also ask if complex properties are necessary conditions for a given conditioned property. So suppose we have the four possible simple conditioning properties A, B, C, and D again, but in addition, we're interested in whether not A, not B, not C, and not D are necessary conditions for a given conditioned property E as well. Then our table would be set up as follows, in which we have the 8 possible conditioning properties, 4 simple and 4 complex, recorded, and we have the given conditioned property recorded alongside in its own column. Now in a typical question, I might give you the presence table for the simple possible conditioning properties and for the conditioned property, E. And using what we know from presence tables, it will be your job to fill in the rest of the table and then to use the whole table to apply what is in this case the direct method of agreement. So if we look at what we've got, from presence tables, we know that the negation of a property is present just in case that property is absent. Suppose then that we record a series of observations as occurrence 1, in which we have the following: A is absent, B is present, C is present, and D is present, and where E is also present. Then, using our knowledge of presence tables for negations, we know that not A is present, not B is absent, not C is absent, and not D is absent. And similarly, suppose we record another series of observations as occurrence 2, in which we have A is present, B is absent, C is present, and D is absent, and where E is also present. Then using what we know about presence tables for negations again, we know that not A is absent, not B is present, not C is absent, and not D is present. Now suppose in this case that these are the only two occurrences we record. Now we've filled in the table, we can use the direct method of agreement to eliminate some possible conditioning properties as necessary conditions for E. So, using exactly the same line of reasoning as before, we see that occurrence 1 rules out A, not B, not C, and not D as necessary conditions for E. Remember, a necessary condition for E cannot be absent when E is present. And occurrence 2 rules out B, D, A, and not C again as necessary conditions for E. So our conclusion, after applying the direct method of agreement, is that if any of the possible conditioning properties are necessary conditions for E, then C is that necessary condition. Okay, now as well as negations of properties, one can also, of course, ask whether disjunctions or conjunctions of properties are necessary conditions of a given conditioned property. There are questions in the assignments that are designed to get you thinking about these situations, but the way you set up the tables is exactly the same as what you've seen here. Use what you know from presence tables to calculate whether a disjunction or conjunction is present or not, and then use the whole table to eliminate the possible necessary conditions. So, what have we seen in this lecture? We've seen the direct method of agreement and how to apply it. And most importantly, the rule we've used all along when we apply this method is this. A property that is absent when a given conditioned property E is present cannot be a necessary condition for E. Now, notice what we've concluded in the examples we've looked at is something of the form, if any of the possible conditioning properties are necessary conditions for E, then such and such a property is that necessary condition. The method doesn't tell us which one of the possible conditioning properties are necessary conditions. It tells us which of them might be and which of them cannot be. A conditioned property, of course, might have more than one necessary condition, so there still might be more to it than what we can tell from our possible list of conditioning properties. Now, what's more, if our initial list of possible conditioning properties doesn't include a necessary condition for the given conditioned property we're interested in, then we won't be able to find it using this method. We would have to go back and use a bigger, more comprehensive list of possible conditioning properties to begin with. Your observations might eliminate everything in your initial list of possible conditioning properties. All this is to say that the logic behind the method of direct agreement is like the logic of a murder detective who eliminates suspects one by one in order to find a murderer. If the detective starts with an initial list of suspects, they cannot be sure they'll eliminate all but one. Maybe the murder was done by two people working together, for example, or maybe the murderer isn't even in the list of suspects that you start with at all. In that case, the detective would have to go back and look for a more comprehensive list of suspects to begin with. All the detective can conclude, if only one of the possible conditioning properties is present whenever the conditioned property is present, then all the other possible conditioning properties are eliminated as necessary conditions. Here's one final question then to consolidate what we've seen here and get us thinking about some of the questions you'll see on the assignments. So here is a table with one occurrence recorded. We're interested in which, if any, of the properties A, B, C, and D are necessary for the conditioned property E. Occurrence 1 has A absent, B present, C present, and D absent, while E is present. So question, what does occurrence 1 allow us to deduce? Okay, so occurrence 1 rules out A and D as a necessary condition for E. Properties B and C are both still contenders for being a necessary condition for E. Now, your job is this, to suggest one other occurrence that would rule out all but one conditioning property. So you have to fill in occurrence 2, such that after occurrence 2, only one possible conditioning property can be a necessary condition for E. So let's pause for a question. So the answer we should have got is the occurrence of A present, B absent, C present, and D present while E is present. That occurrence rules out B. So then A, B, and D are ruled out by occurrences 1 and 2. And that leaves only one possible conditioning property, C, as a contender for being a necessary condition for property E. Now, of course, you could also have come up with an occurrence that ruled out C while leaving B, but that wasn't one of the multiple choice options on the question, so there was only one correct answer. And you can expect this style of question on the assignments, so that's why we took a look at one here. Okay, so next time we'll look at the second of Mill's methods, the inverse method of agreement. We'll look at what it does and how to apply it. So have a go at your self-reflections, and I'll see you all in the next installment.